Great, thank you. Okay, hello everyone. My name is Andre Cleaver. I'm a PhD student at Tufts University, and I'll be presenting my submission titled RAIN, a visual calibration tool using augmented reality. So there are three main motivation points behind this work. The first, robots need accurate visual information to operate successfully and safely in the public environment to support their navigation, localization, and obstacle detection capabilities. The second is robots are using computer visual algorithms to identify these objects from raw data. So calibrating a robot's visual pipeline requires expertise to adjust any misperceptions. So for example, the two images on the right kind of show cases where the robot mistake the number of objects in the field. The top object, you're seeing the robot mistakes 3 objects for 2. And bottom image, the robot mistakes 2 objects for multiple objects. So addressing this issue often requires an expert who kind of knows where in the code to look for and which parameters to adjust. That sort of acts like fine-tuning the algorithm. So we believe this process can be made easier and even extend the calibration test to non-experts. So the third point is that there is a need for a tool that simplifies the calibration process, and our approach is relating the parameter changes to projected visual graphics. So our proposed solution is RAIN, an augmented reality app that connects to a robot and its computer visual algorithms to a smart device such as a smartphone or a tablet. So using ROS and Unity, a user can control the parameters and see their changes. But more importantly, you're seeing the changes to a robot's perception of the environment. So in the image to the right are just 2 screenshots of the RAIN app. The robot is running a cylinder model detector script, taking a point cloud dataset as input, and the algorithm is looking for a cylinder model that meets the specified dimensions within the code. So as a proof of concept, the minimum radius parameter can be changed. I linked it to 2 buttons on the interface, and I do change that to detect the orange cup, which is a radius about 4.5 centimeters. And the robot will be able to display the segmented point cloud once it detects that. So as a quick demo, so at the bottom of the image, it's the robot step camera along with a target image to align the perspectives of the robot and the human when visualizing the point cloud. So right now the robot doesn't detect any cylinder with a minimum radius of 4 centimeters, but until I increase that to 4.5, that's when the robot is able to detect the cylinder, and it sees it as like 7,000 points. And in addition, I just added as a couple of features by changing the particle size and color for the user preference. So the couple of things that I've learned from this project is that certain data types really large in size, such as point clouds, which may cause latency issues during a calibration task. So that can be problematic. A second is visual clutter issue, where you're just overwhelming the user with so many rendered visualizations. So that kind of leads to a need for an adaptive visualization to address how much information do you want to show an individual at any time. And lastly, there's the general rule, is there a general rule to represent sensor data as a visual graphic? And in my case, it will be, is there a more fitting way to represent point clouds in AR? So in a future direction, we want to explore the calibration pipelines for other algorithms. For example, the image on the right, figure A, kind of shows the positions of where the robot thinks it is in a localization process. And figure C, you're looking at a human detection algorithm. So we want to see if we can explore if participants can assist the robot by making any corrections if the robot is making a mistake. And to the image to the left, we're looking at exploring robotic education for using AR for kids. And we're seeing at creating learning objectives that involve kids debugging the robots by visualizing their sensor readings. In that image, you're seeing a ED3 robot from Lego, and you're seeing one of the sensors being displayed. So in that case, that concludes my presentation, and you can ask me further questions in the post session. So thank you.
Thank you, Andre. And then I made a slight mistake. We won't be going in paper order. We'll go based on the order of the program listed online. So next is Jordan Alspaugh, I believe. Jordan, are you ready?
Yeah, Greg's going to be presenting.
All right, awesome. Thank you.
Sorry, I couldn't unmute. Okay. Hello, everyone. My name is Gregory LeMagerie. I'm a master's student at the Human-Robot Interaction Lab at the University of Massachusetts Lowell. And today I'll be presenting our paper, Implementing Virtual Reality for the Teleoperation of a Humanoid Robot. There's been a lot of interest in using autonomous robots in a variety of fields. And autonomous robots have seen success in some environments, such as warehouses, but it's still difficult to automate scenarios such as bomb defusal, where we have very little control over the environment, where tasks are complex or varied, or if there's unforeseen circumstances that are likely to arise. And thus it's very important that we have well-designed human-robot interaction methods that enable us to maximize both the strengths of the operator and the robot. And so we have designed a VR interface that enables an operator to control a Valkyrie R5, which is a humanoid robot from NASA, from entirely within VR. And the operator will not need to take off their VR headset to use a supplementary interface. When designing our interface, we looked to the interfaces used in the DARPA Robotics Challenge for inspiration. The DARPA Robotics Challenge was a competition where teams competed to perform tasks using a humanoid robot. In particular, we were interested in the control methods and the information conveyed through these interfaces. We also took inspiration from the control methods and user interface elements used in various VR video games. We had previously presented our interface at VAM-HRI 2018, and since we've made a number of improvements that I'll be discussing today. When we were adding our user interface elements, we realized that we can group them using the three principal categories for mixed reality interaction design elements that was proposed by Williams et al. The first being virtual artifacts, which are objects that the robot or the operator can manipulate. On the left, we have our goal marker, which is a navigation goal for the robot. And on the right, we have footstep markers, which I'll be discussing later on. Next is user-anchored interface elements, which are interface elements that are anchored to the operator's coordinate system. On the left, we have our heads-up display, which we use to display critical information, which includes a ping to the robot or a battery status alert. And on the right, we have our virtual wristwatch, which is a heads-up display that's anchored to the operator's wrist and is activated when the operator extends the wrist out as if they were looking at their wristwatch. This can be used to display things such as various control methods, which I'll be discussing in a little bit. And finally, we have environment-anchored interface elements, which are interface elements that are anchored to either the robot or the world's coordinate system. On the left, we have our point cloud visualization. These point clouds were generated either through a sensor on the robot or an external sensor in the environment. And this enables the operator to understand the environment around the robot. And next, we have our robot model and virtual tablets. The virtual tablets here are being used to convey external camera streams. In order to control a robot from entirely within VR, it's important to offer a variety of different mobility control methods. Our first mobility control method is a joystick interface, which is very similar to that of an RC car, where the operator can press down on the joystick, which will command the robot to move. And then we offer two mobility methods where the operator can specify a goal, which will then be sent off to the robot's footstep planner. The operator can specify a goal either by pointing to a location in the environment or through a minimap interface, which was designed modeled after minimap interfaces that are used in real-time strategy games, where an operator can click on a location on the minimap, and that location will be sent off to a goal to the robot. In both of these control methods, footstep markers will be generated to show the operator the robot's planned path, and the operator has the option to modify the position and orientation of each footstep before they confirm the plan. It's also important that the operator has the ability to manipulate the robot's joints. And our first joint control method is a grab and drag interface, which is very similar to the interface used in Move It, where an operator can grab onto one of the robot's joints and drag it to their desired location. Next, we have a direct control method, where the robot will mimic the operator. In this control method, the position of the operator's hand and the position of their fingers if they're wearing a VR glove is sent off to the robot's inverse kinematic solver. There's also situations where the operator may not want to rely on the robot's inverse kinematic solver. So we offer a slider interface where the operator can control each joint individually. In the future, we plan to compare our VR interface to a keyboard and mouse interface that was designed based off of the interfaces used in the DARPA Robotics Challenge. In particular, we're interested in investigating how the operator understands the environment around the robot and the total workload that the operator experiences when using both of these interfaces. We'd also like to identify weaknesses in our VR interface and explore using our VR interface to control a variety of different robots, including robots with a single end effector or a different mobility platform. And if you have any questions, I encourage you to talk to us at our poster session, or you can contact us at one of the emails provided. Thank you.
Thank you, Greg, or Gregory. All right, next paper is paper 13, Telerobotics via an efficient immersive virtual reality architecture. Anyone here to present that? Couldn't find the main author. All right, we'll skip over that one for now, and then I'll see if they are here by the end. The next person, I believe, is named Tran. I believe I saw you here somewhere. Are you ready to go? You're muted right now. Here, I'll mute you. There you go.
Thanks. Yeah, let me share my screen. Share screen. Share screen. Can you all see my screen? Anyone? Okay, good. Right, hello, my name is Nyan Tran from School of Mines, and today I'll share with you that what the Mirror Lab and I have been working on in exploring mixed reality robot communication under different types of mental workload. As robots begin to assist humans in increasingly diverse environment and tasks, communication will become one challenge that robot will face in working with the human partners. So let's imagine ourselves in a scenario, like if we are a drone and we need to communicate with a human teammate in a search and rescue mission about the location of the victim, then what can we do? Well, first, we can probably use purely natural language, such as I found the victim behind the tree from the left in the clump of tree, blah, blah, blah. It's very verbose and unnatural. Like usually human would use like pointing gesture, or also known as didactic gesture, to draw our teammates' attention to such a hard to describe region of interest. So we can use didactic gesture, but what about these armless robots? Like these drones, they don't have arms. What can we do? Well, we can attach a physical arm, which could be both expensive and likely mechanically impossible. And actually, if you listen to one of the paper from our lab by our teammate Jared, hope he's here, and you can find out more about his work in attaching a virtual arm to a robot. So with the recent advancement in augmented reality, we have a new channel of interface that we can communicate with these robots. So we can overlay virtual information on top of the real world scenes. So let's go back to our previous example. What if we pair language with visual gestures, such as arrows or circles, so that the robot target reference are picked out in the human field view? And we hypothesized that doing so can simplify the robot's language. So instead of saying a complex and verbose description, we can just say, I found a victim over there, and draw the arrow to the human to direct the attention. So AR is cool, but there are several other contextual factors, such as cognitive load and perceptual load, that we need to pay attention to. when you think of cognitive load, it means that you cannot process extra information. So like if you're in a big lecture hall and you are experiencing cognitive overload, you might not be able to understand the lecture anymore. Perceptual overload means that, let's say that if I asked you to search a water bottle in a big table with a lot of similar looking water bottle, you might experience visual overload because you don't know where the target bottle is, because there are so many similar looking bottles. Similarly, in auditory perceptual load, you might hear a lot of like similar noises or sound that you cannot distinguish the instruction. So in the context with high visual workload, if we ask the robot to, if the robot wants to communicate its intent when the human is under high visual workload, probably it might not want to use visual gesture because the human might not be able to process extra visual information, but what if we can use spoken language? Or in the context with high auditory workload, perhaps we don't want to provide more spoken instruction, but what if we can use AR to communicate? There's these kind of assumption or factors lead into these 4 different hypotheses. First, user under high visual perceptual load will perform best when robot rely on complex natural language without mixed reality data gesture. Second, users under high auditory perceptual load will perform best when robot rely on mixed reality data gesture without a use of complex natural language. And third, user under high working memory load will perform best when the robot rely on mixed reality data gesture without the use of complex natural language. And lastly, users under low overall load will perform best when robot rely on mixed reality data gesture paired with complex natural language. So in order to answer this hypothesis, we designed a human subject experiment in which the human participant were asked to play a pick and place game in AR. So we have the robot Pepper across the table, and we ask the human to play this game in mixed reality. We have 3 different communication strategies that we want the human to work with the robot. First, the robot only uses verbal instruction. Second, the robot augment the instruction with AR and use symbol language such as, can you please pick that cube over there without describing the cube. And in the third strategy, the robot uses complex language such as, can you please pick the red cube and place that in the blue bin. So very descriptive. Earlier, we mentioned that we want to figure out how these communication strategies are affected by mental workload. We does also jointly and systematically vary the mental workload by adjusting the properties of the virtual objects. And if you want to find out more, you can check out our paper. So given 3 different communication strategies and these different workload, we come up with 12 different within subject conditions. We did measure both subjective measurements and objective measurements. For subjective measures, we use the NASA TOX, like Stephanie mentioned earlier. For objective measures, we just log the user's accuracy and reaction time while they play this game. So as a result, we found that we could not find the difference in perceived workload and perceived effectiveness. This could be due to task difficulty, or the reaction time was not large enough for the participant to notice. However, what we did find were that there is a complex interplay between communication style and cognitive load. And AR plus complex language result in best task performance in most workload conditions. And AR plus symbol language reduces the reaction time when the users are under high working memory load. I'm going to skip this part because I know that I'm kind of running out of time. But this graph simply shows how our different users play the game, and you can see that there are lots of red dots in here, which means that lots of users fail, which imply that our task could be difficult for users. So in future work, we want to use a different approach to, instead of subjectively measure the cognitive load, we wanted to use some sort of objective measurement, such as a functional infrared spectroscopy, which is like a brain sensor to actually measure the workload. So that is our future direction. And if you have more questions, I can answer them in the chat after.
Thanks. All right, next person's from the Wait, I'm Tagged paper. I'm not sure who is presenting. I saw a couple people from that paper in the Slack. I think it is. Call a couple of those people out real quick.
This is Michael Nowitzki. I was hoping to present the paper. How do I share my screen with you? It's telling me that it's blocked.
Let's see here. I'll just do this. Can you share your screen now?
Yes, thank you.
Yeah, of course.
Sharing it on the wrong screen. I'll be right back. There we go. Can everyone see my screen? Can everyone hear me? I'm getting some thumbs up. Great, great.
Yes.
All right, so I'm here to present the paper Wait, I'm Tagged Towards Augmented Reality and Project Aquaticus. I'm representing several co-authors here. Our cadet Nicholas Frank has actually graduated. This was his work that he started in January. Krista Chouar, myself, Michael Nowitzki, I go by my nickname Misha, and Christopher Corpella. So, let's see. The reason we started looking at the work we were about to describe is because of Project Aquaticus. Now, what you can see here is what we were hoping to do was to look at how humans and robots can team together to do complex and dynamic competitions. So in this case, we used humans in motorized kayaks and robots that were marine surface robots to be teammates. And we put them in a game of playing a competitive capture the flag. So you could talk to your robot by saying commands such as blue 1 defend, blue 1 attack, in which the robot would autonomously avoid obstacles and other players, try to grab a virtual flag and bring it to score at its own home base throughout the game. You can see that it was a really great environment being out on the water, and it was a lot of fun. So just recently, we presented last month at the presentation Virtual and Augmented Mixed Reality, which was supposed to happen in Denmark, but it happened virtually. We showed the work of moving to take the Project Aquaticus simulator and turn it into a virtual reality experience. Now, the reason we did that was because our previous simulator was a top-down view that would give you an omniscient view of the world and didn't quite reflect what people experience on the water, which was you only had the view in front of you, you only got audio interfaces, and you didn't quite know what was going on if you lost track. But what does this allow us to study? Well, it actually allows us to study quite a bit. And one of the things that came up during our experiments was that our participants would come off the water and say things like, I had no idea what the robot was doing. I had no idea what was happening. And in fact, in the title, it says, Wait, I'm Tagged. And that's because participants would be at the opposing end of the field trying to grab the opponent's flag and then come back on the radio like, why on earth can I not grab this flag? And we had to tell them, you're tagged, you know, and we couldn't quite tell them, listen, you just missed the message because you should have heard it like 5 times by now. But they were somehow missing that situational awareness. So how do we address that? And so our research question is, how can we improve our participants' situational awareness and reduce their cognitive load while doing human-robot teaming? And for this work, we're looking at using augmented reality on top of our virtual reality headset to try out those things. Now, here you can see a mock-up view. Unfortunately, we were going to try some of these things with participants. However, COVID-19 came across and everyone had to go home and we couldn't quite do it in person. So what we see here is a mock setup. What the virtual screen you see has the opponent vehicles, such as the kayaks and the black robots. But in green, you see highlighted our augmented reality ideas. So one of the ideas we want to expand on is the list of commands that you see in the top left. Now, what we had was a little card for people that we would keep in their boat as a list of commands they could talk to their teammates. However, some people would completely forget and stop the game and stop looking around and doing object collision avoidance, and they'd look down at their boat just staring at the list of commands. We're like, well, what if we put that in the augmented reality? Maybe that'll help. Other thing was that we wanted to make sure that people understood on their teammates who was tagged where the flag was, if someone had the flag or not. The other thing we thought about was trying to indicate where people were in relation to their own boat. So what we noticed a lot is that if someone was really comfortable looking around, they had pretty good situational awareness. But if they were locked really focused, then they would lose track of what might be around them and different things that they could respond to. So our plan in the future is to actually do experiments here on Post, where we have cadets try out the different versions. What we want to be able to do is some user-centered design, where we have feedback from people. One thing we definitely don't want to do is overwhelm them with too much information or clutter up their scene too much. We definitely want to measure the cognitive load. We just heard someone talk about the NASA TLX. I like using other measures as well, such as maybe galvanic skin response. I'm not quite sure. Another thing we want to measure is situational awareness. So maybe we'll take a time out and ask the person, okay, what's happening right now? And vary what they see in augmented reality and see if that makes an impact. Of course, I want to thank my sponsors throughout the year and all the people I've worked with to make Project Aquaticus a success. I look forward to talking to you guys at the poster presentation. Thank you.
Thank you so much. I believe Jared is next. Jared, I can't hear you. Can anyone hear Jared? No, I don't think anyone can hear you. It's always the most fun part of Zoom meetings of, can someone hear you? And I've had it, I just had it from the first session where I couldn't hear it.
Okay, I think, oh, I see my screen highlighting. There we go. Okay, perfect. I'm gonna share my screen over here. That looks right. Okay, everyone can see. Oops. All right, everyone can see the screen?
Yep.
All right, perfect. Well, my name is Jared Hamilton, and I had the opportunity to explore the trade-offs between performance and positive social perception of mixed reality deictic gestures in robots. The motivation of this is to explore how we can use mixed reality to enhance robot gestures. This enhancement could offer benefits to the user, such as higher task performance in addition to a higher social perception. We've determined two factors that would influence human task performance and social perception. The first is the mixed reality deictic gesture type. In my experiment, we used two different types. This is the mixed reality method a robot uses to non-verbally highlight a target object on the user's AR head-mounted display. The second factor is object distance. We figured that varying the object distance would add challenges to certain types of mixed reality gestures. We decided to explore two different mixed reality gesture types, and this is from Professor Williams' taxonomy of mixed reality deictic gestures. The first is an arrow gesture, which is just circling a target referent, in this case, drawing an arrow over the target. And then the second type was an arm that was mounted on the robot itself, which would be classified as an ego-sensitive allocentric gesture. Our first hypothesis was centered around performance. We predicted that when the robot used the arrow gesture at the target object, the human subject would have a shorter reaction time and higher accuracy compared to when the robot used the arm gesture. This was because we thought that the subject would generally have a harder time mentally tracing the trajectory of where an arm was pointing, and they would also have to look back and forth between the robot and the target objects. Our second set of hypotheses were centered around social perception. We believe that when the robot used an arrow gesture, it would have lower social perception compared to the arm gesture. The components of social perception we decided upon are listed on the right, such as anthropomorphism, social presence, likability, competence, and warmth. Their definitions and the following questionnaire for them were pulled from the Godspeed and Rosas papers. To assess these hypotheses, we designed a human study that considered two different types of mixed reality gestures. We compared two types, the arrow and the arm, as you can see here. In that picture, it shows how we mounted the augmented reality arm on the turtlebot, and then with the arrow would just move to whatever target object it was pointing at. The experiment layout consisted of 4 counterbalance blocks of different experimental conditions, which were dictated by the following independent variables. We have gesture method, and then object distance. The experiment method is pretty straightforward. The subject faced the turtlebot for each trial. The robot would gesture at one of the 3 different colored virtual spheres as shown in the GIF. After the robot gestured at a sphere, the user tapped on the sphere they believed was gestured at. This cycle was repeated 10 times, then the trial was over. After each trial, the user was instructed by the HoloLens to fill out 26 survey questions that inquired about their experience with the robot. This is the questionnaire that was used to measure social perception. There were 4 trials total, each one testing a different experimental condition. So our first hypothesis was that when the robot used the arrow gesture, the subject would have a higher accuracy and shorter reaction time. Our results showed a strong degree of evidence that humans did indeed perform at higher accuracy, strongly supporting our hypothesis. Our results also showed a strong degree of evidence that humans did indeed have lower reaction time for the arrow gesture as well. Thus, the second part of our first hypothesis is also confirmed. Our second hypothesis was that when the robot used an arm gesture, it would have a higher degree of social perception than when it used the alternative gesture. Our first measure was anthropomorphism, and our results showed extreme evidence that when the robot used the ego-sensitive gesture, it did indeed have higher anthropomorphism. Thus, that part of the hypothesis is also true or proven. Our second measure was social presence, and our results also showed extreme evidence, again, that when the robot used the arm gesture, it had a higher social presence. And then here are our remaining subjective measures, and you can see their corresponding Bayesian factors. Likability was moderately supported, and then warmth and competence suggests that we need more data for that. So overall, our results show a clear trade-off between positive social perception with an arm gesture method and then better performance with the arrow gesture method. When the robot used a virtual arm to gesture, they performed at better reaction time and accuracy. And then again, with the arm, they had much higher social perception, which has been shown to have more long-term benefits for human-robot collaboration. So that is not something to be quickly neglected. And this, of course, presents a design challenge for engineers as we want to be able to achieve the best of both worlds. So in future work, it would be useful to experiment with more complex scenarios. For example, what if the human-robot team involved multiple robots that all need to gesture at objects in the user environment simultaneously? This might show a clear fall-off in performance when using an arrow gesture method. Sure, you could color code or something like that, but there's no clear way to trace the arrow back to its parent robot. An arm gesture, because it's egocentric, it's attached to the ego, which is the robot, and so there's no problem tracing it back to its source. However, having to track multiple sources of robots, having to test this imposes a significant computational burden on the HoloLens. It doesn't really like tracking more than a few AR tags, and the AR tags I'm using mounted on these turtle bots are actually the multi-tag formations. The one I used in the experiment had, it was a cube AR tag without the bottom, and so that was enough for it already. Yeah, so main takeaways, there are clear trade-offs that exist between our different gesture methods, which of course presents a design challenge. To more clearly understand how to approach this challenge, we need to further explore these gestures in more complex scenarios for future research. Thank you for listening, everyone. If you have any questions, I'd be happy to answer them in my Slack channel.
Thanks, Jared. And I think the last one is going to be, I think Nicholas Woodward is here. You all
Yep.
good to go?
Hi. Okay, one sec. Let's see. Does everyone see everything all right? Okay,
Yep.
cool. My name is Nicholas Woodward. This research is on exploring interaction design considerations for trustworthy language-capable robotic wheelchairs in virtual reality with the Mirror Lab. So our research takes interest in language-capable wheelchairs, which have a lot of interesting considerations. They can be seen as vehicles, which are tools to get the user from one destination to another, but they can also be seen as companions, where we generally expect some sort of social behaviors. And then there's also this concept of paired autonomy between the wheelchair and the human, where the wheelchair's actions have an effect on the human's autonomy and vice versa. So there's been lots of previous investigation into the dynamics of trust and interaction between humans and machines, humans and robots, and humans and vehicles. In our research, we focus specifically on the requirements for trust between humans and language-capable intelligent wheelchairs, and also how these differ from requirements for trust between humans and non-vehicular mobile robots. This brings into account when a robot provides an explanation for its actions, and in addition to that, the transparency of that language, or whether or not it is clear and useful. So here are two situations that we wanted to examine in our study. In the first, Alice is following her language-capable robot, which means they have independent autonomy. When the robot makes a decision, it does not directly affect Alice's autonomy. And that contrasts to when Alice is riding her language-capable wheelchair, where the actions of the wheelchair affect her own autonomy. And in both cases, the robot takes an unexpected detour. So you can see with these two situations that there are varied trust requirements. This can be addressed with two different types of explanations. The first are proactive explanations, which are explanations generated before an action is taken. And then there are reactive explanations, which are provided only if the user asks the robot to. So our study had 4 different conditions that utilize this situation with those different communication methods. With the general premise of the experiment, in an office environment, a participant is tasked with delivering papers to different rooms, different office rooms. Depending on the condition of the experiment, the participant sits in and commands an autonomous wheelchair or follows a ground robot using arm swinger, which I'll describe in a bit. So on this graph over here, the red and blue paths are the first 2 routes that the participant will take, which follow the same path along the environment. And then the orange path is the third path, which is the detour. And depending on the condition, the robot will either provide an explanation proactively. For example, I detected a water puddle down this hallway, so I will take another route. Or they will only provide an explanation if the user requests one. So the reasoning for us using virtual reality in this experiment was that it played a very important role in providing a safe and controlled test environment. It allowed us to use a virtual rather than a physical wheelchair and ground robot, which first of all ensured the safety of the user, as well as reduced material requirements. And it also allowed us to easily introduce elements like a water puddle in the hallway that is the inspiration behind the robot needing to take a detour. And we can also replicate perfect autonomous behavior, or relatively perfect, of the robots using a Wizard of Oz experiment setup where a experimenter is controlling the robot in response to the commands of the user, but in a different room so that the user doesn't realize this. We examined several potential methods of user motion control in virtual reality, and we decided on the arm swinger system, which if you see in the bottom right corner of this slide, basically the user swings their arms back and forth to mimic walking in real life, albeit in an exaggerated manner. And we concluded that it provided the highest level of immersion as well as the lowest level of motion sickness. So upon each return to the office, actually I'll show that where to go? There you go. So each time they follow a route, they will return to the office. A survey is administered with Likert items on a scale of 1 to 5, designed to examine reliability, capability, and trust. Our results so far suggest that proactive explanations may be more effective than reactive explanations, and that this may be especially true for wheelchairs due to their paired autonomy. However, more data is needed in order to confirm this effect. Our study was cut a little short by COVID, so cool. So yeah, that's all I have. My name is Nicholas Woodward. I'm happy to answer any questions in the Slack channel. Yeah, thank you.
Thanks, Nicholas. All right, I